We conceptualize the genome as a physical, spiraling double helix. But when downloaded, it's not a biological molecule. You get flat, linear text. Standard sequence formats like FASTA and FASTQ strip away all three-dimensional biological complexity. The 3 billion base pairs of the human genome are reduced to endless strings of basic ASCII characters, A, C, T, and G. Searching for a specific protein-binding motif inside 3 billion letters seems like a simple task for a standard find command. It fails because biological sequences are rarely uniform. Standard programmatic string matching, like Python's .find method, requires absolute one-to-one parity. If a sequence contains a single point mutation or a natural variable region, a strict search algorithm returns a false negative. The algorithmic solution to this strictness is regular expressions, or Regex. Regex is not an independent programming language. It is a universal syntax for pattern notching, acting as an analytical layer over text-based data. Its utility in bioinformatics comes from its ability to translate biological ambiguity into strict mathematical search logic. We will build this logic from the ground up, starting with basic literal matches, expanding into complex pattern logic, and deploying within a Python pipeline. In computational biology, you cannot analyze what you cannot accurately locate. Mastering Regex provides the precision required to navigate the vast digital records representing biological life. The foundation of Regex is the literal match. You input a specific string of characters, and the engine scans the data for that exact sequence. If you are looking for a highly conserved region, like an EcoRI restriction site, a literal search for GAA-TTC works. The biological sequence is predictable and invariant, but most biological motifs feature degenerate nucleotides. The engine needs a way to accept multiple valid characters at a single genomic coordinate. Character classes use square brackets to achieve this. The pattern G-AT-C accepts A or T in the middle, capturing GAC and GTC, but ignoring GCC. Chaining these maps a full consensus sequence, specifying acceptable variations at each coordinate to match known biological mutations. You can also simply invert this logic. Placing a caret symbol inside the brackets excludes specific nucleotides. This allows an analyst to bypass documented mutations while capturing all other variations. Instead of writing dozens of brittle if-else statements to account for every possible point mutation, a character class condenses biological degeneracy into a single line of search logic. Positional ambiguity is only the first layer. Many biological motifs vary in the actual length of a region between samples. Transcription factor binding sites frequently contain variable spacer regions. Two highly conserved domains might be separated by a stretch of DNA that ranges anywhere from 2 to 4 bases in length. Quantifiers, defined by curly braces, capture this by setting minimum and maximum lengths. Combining a character class with a quantifier creates an elastic parameter. The modifier 2, 4 stretches to validate gaps of 2, 3, or 4 bases between conserved domains, ignoring anything else. When the length of a sequence is entirely unknown, shorthand quantifiers like the asterisk for 0 or more and the plus sign for 1 or more allow the search to continue until the next condition is met. These shorthand symbols default to greedy matching. Without strict boundaries, a plus sign might capture an entire chromosome instead of stopping at the nearest end of a specific motif. Quantifiers give algorithms biological flexibility. They provide the logic necessary to capture motifs, even as they stretch and mutate across generations. A raw DNA sequence is analytically useless without its associated metadata. The identifiers for patient samples, read quality scores, and chromosomal coordinates are all stored in structured headers that require precise extraction. This metadata is packed into dense, inconsistently formatted header lines. Anchors provide positional context. The caret and the $sign lock a search strictly to the absolute beginning or the absolute end of a string. This precise positional locking prevents false positives. An ID number anchored to the line start won't be confused with a quality score at the end. Once anchored, capture groups, written as parentheses, extract the targeted text. The engine reads the string but outputs only the data trapped inside. Applying these capture groups allows for the automated renaming and sorting of millions of sequences based on their header metadata. Anchors and capture groups separate the biological signal from the operational noise. They transform messy text files into structured, queryable databases. Regex syntax requires an execution engine to process the data, which in bioinformatics is typically Python. Python handles this via the built-in RE module. This is the wrapper that deploys your regex patterns against actual biological variables. The simplest tool is re.search. It acts as a binary check, scanning the text and stopping the moment it finds the first instance of a motif. To count the total frequency of a motif across an entire read, re.findAll. Scans the full string and returns every match it encounters. But findAll only returns the matched string itself. For downstream mapping, bioinformaticians need the exact genomic coordinates of those matches. re.findIterator. Provides this context. Instead of a list of strings, it extracts the indices, the precise start and stop coordinates for every match in the sequence. Running a complex regex search over a 3 billion base pair genome loop by loop creates a computational bottleneck. Re-evaluating the pattern on every iteration wastes significant processing power. This chart shows the exponential spike for uncompiled regex loops versus the flat, efficient line of r.compile. Caching the pattern in memory as a dedicated object drastically reduces compute time. Finally, r.sub enables mass data cleaning. It allows you to strip out unwanted characters or standardize formatting across legacy datasets with a single command. The R module bridges the gap between theoretical pattern matching and actionable data engineering. It turns static matches into manipulable data structures. Let's look at how these compiled patterns operate in real-world bioinformatics pipelines. In automated primer design, Regex scans for target regions and extracts the flanking coordinates needed to generate exact primer pairs. When processing general feature format files, capture groups sort messy, concatenated feature columns into clean, readable data frames. And complex variant nomenclature, like an HGVS string denoting a specific point mutation, is instantly parsed into distinct position, reference, and alternate components using compiled patterns. These operations execute millions of times per second across immense datasets, instantly turning absolute chaos into perfect order. Every major bioinformatics software suite relies on this underlying logic to function. Biological databases are ultimately just text, and text bows to the rules of regular expressions. Modern genomics produces data at a scale that breaks hard-coded logic. By adopting pattern matching, you turn a mountain of biological text into a searchable, actionable library. Subscribe for more from BioInfoBytes.